10 billion light-years wide. That is the size of the largest thing astronomers have ever mapped, and the reason they still call it the biggest structure in the universe, instead of what it actually is. Nothing that size has ever been able to hold itself together. The universe is about 13.8 billion years old, and even light has not had time to cross a region that wide. And gravity, the only force patient enough to build something as large as a galaxy, needs exactly that kind of contact to hold anything together. So when the word structure gets used at that scale, it doesn't mean an object anyone could point to as a single thing. It means a pattern, a place where galaxies are more common than average, or where a great many of them are quietly drifting toward the same stretch of sky, the way rain drifts toward the same river without the drops ever touching. It is real, it is measurable, and it is not gravitationally bound. Not one object, but a pattern in how part of the universe happens to be moving. The Milky Way is caught inside one of these patterns right now, carried along with well over 100,000 other galaxies toward the same corner of the sky. A flow astronomers can measure, have named, and have mapped using almost the same method water uses to find a river. Not what is standing still, but what is moving and toward where. If this is the kind of night you return to, subscribe. It helps this quiet universe keep growing. So, let's begin. Start with the ordinary case, the one every one of us already lives inside. A galaxy holds together because its stars are close enough and numerous enough for their combined gravity to overpower the general expansion of space. The Milky Way is not drifting apart, neither is Andromeda, our nearest large neighbor, and neither is the small crowd of smaller galaxies around both of us. Called the local group, gravity has had enough time and enough strength at that range to bind these galaxies into one long-term system. Andromeda itself, the nearest large spiral to our own, has had its motion toward us measured directly, using the same redshift technique behind almost everything else tonight, only reading blue shift rather than redshift this time. The signature of something approaching rather than receding. Current measurements, refined over decades and checked against the sideways motion Andromeda shows across the sky as well, suggest the two galaxies will finish that approach several billion years from now by merging into a single, larger galaxy. That is a bound future, already written into the mutual pull measured between the two, independent of anything about the wider patterns the rest of tonight is about to describe. Now step back much farther, to the scale where the word supercluster starts to apply and the picture changes. In 2014, a team led by the astronomer Brent Tully published a study in the journal Nature that gave our home region of the universe a name for the first time. Laniakea, a Hawaiian word chosen with the help of a Hawaiian language professor, consulted specifically for the task to mean immense heaven, chosen deliberately over a more clinical catalogue name, in recognition that this particular basin happens to be the one holding every star, every planet, and every person who has ever measured it. It was not a discovery of new galaxies. Every galaxy involved was already catalogued. What Tully and his colleagues did was map how all of them were moving, not just their positions but their velocities, corrected for the general expansion of space, so that what was left was the leftover motion, the part of each galaxy's speed that comes from being pulled by something nearby rather than simply carried outward by the growth of space itself. When they plotted that leftover motion across a large volume of the local universe, a shape appeared that had never been drawn before. Galaxies on one side were drifting one way, galaxies on another side were drifting a different way. Somewhere between those two flows there had to be a dividing line, a place where the pull in one direction exactly balanced the pull in the other. The same way a ridge of high ground divides a rainstorm into two rivers. Tully's team borrowed the mathematics that hydrologists already use to map watersheds on Earth and applied it to the sky. The boundary they found using that method is not a wall or an edge you could touch. It is a set of positions in space, and in the flow of galaxies through that space, where the direction of drift changes sides. Everything on our side of that boundary belongs to Laniakea. Everything past it belongs to a different basin, with its own name, its own center of pull. The boundary itself is not drawn on a photograph. The way a coastline can be traced on an ordinary map, it exists only in the mathematics of the velocity field. A computed surface, built entirely from how galaxies are moving, rather than from how they look, that happens to separate one basin's worth of drift from its neighbors, fly through the region in a spacecraft equipped only with ordinary cameras, and nothing would visibly mark the crossing. The galaxies would look the same on either side, at the same average density under the same dark sky. Only a velocity measurement, taken and compared carefully the way Tully's team did, would reveal that something about the destination each galaxy is heading toward had quietly changed. It is worth being precise about what word to use for that boundary, because precision here is doing real work rather than just sounding careful. Astronomers call it a basin of attraction, borrowing the phrase directly from the mathematics of dynamical systems, where it already meant exactly this. The full set of starting points that, followed forward under a given set of rules, all end up converging toward the same outcome. A basin of attraction is not a container. Nothing is inside it the way water is inside a cup. It is a description of destiny under a rule, applied here to gravity instead of to a river system, and to galaxies instead of raindrops. That is the specific, checkable sense in which Laniakea is real. It is not a guess about how big our neighborhood looks. It is a map of which way well over 100,000 galaxies are actually moving, built from real velocity measurements, with a boundary defined the same way a geographer defines where one river system ends and another begins. And by that same definition, Laniakea is not bound together the way the local group is bound together. Its outer galaxies are not orbiting its center. The way planets orbit a star, they are simply drifting the same direction. For now, along a slope in the gravitational landscape that the expansion of the universe is slowly flattening out from underneath them. Given enough time, that shared drift will not hold. The pattern will not survive the way a bound system survives. It will thin out, the way a river system can shift when the land itself changes shape. Consider, for a moment, what it actually took to notice that pattern at all. Nobody can watch a galaxy move. A galaxy hundreds of millions of light years away sits, for any human lifetime, exactly where it appears to sit, drifting far too slowly. On any time scale, a person could sit and observe for the motion to show itself directly. What Tully's team measured instead was speed inferred from light, the stretching of a galaxy's light toward redder wavelengths, a signature so reliable that it has been the workhorse of cosmology since the 1920s, compared very carefully against an independent estimate of how far away that galaxy actually is. The difference between the two numbers, done galaxy after galaxy, tens of thousands of times over, is what let a pattern spanning 500 million light-years become visible to a species standing still on one small planet that has never seen it happen and never will in any single human lifetime. That is worth pausing on, because it says something about patience that the rest of tonight will lean on more than once. Nothing about Laniakea, or the Great Attractor, or any of the larger patterns still ahead, was found quickly, or found by looking harder in the ordinary sense. It was found by accumulating thousands of small, careful measurements of light that had already been traveling for millions of years before it ever reached an instrument capable of reading it, and only letting the pattern emerge once enough of those measurements existed to compare against each other. A single galaxy's motion says almost nothing. 100,000 of them, compared and mapped together, say a great deal. It also helps to say plainly what tonight will not be. It will not be a list of ever bigger numbers meant to leave the listener dizzy, and it will not spend its time arguing that everything astronomers have written about the larger structures is wrong. Most of it is careful, honest, and well-earned. The correction sitting underneath tonight's title is smaller and quieter than that, and, in its own way, more useful. Not that these patterns are false, but that the word structure has been asked to do a job at the largest scales that it was never built for, borrowed from a much smaller, much more solid everyday world of tables and rocks and walls a person can actually lean against. None of this changes what happens next, only how it should be received. What comes over the following chapters is not a countdown of ever larger discoveries meant to impress. It is closer to a single question, followed carefully, at larger and larger distances, each answer changing very little about the last one, only adding one more piece of a picture that was already, from the very first minutes of tonight, mostly in view: gravity, patient and real, building what it can, and stopping, honestly, exactly where its reach runs out, somewhere behind the disk of our own galaxy, in a direction astronomers still describe, half seriously, as the zone of avoidance. There is a patch of sky the Milky Way itself gets in the way of. Our galaxy is a flat wheel of stars and dust, and we live inside it, off to one side, which means that whenever we try to look straight through its thickest part, dust and starlight block the view the way fog blocks a coastline. For decades, an entire slice of the extragalactic sky was, for practical purposes, missing from the map. The very idea that our galaxy belongs to some larger regional grouping is older than Laniakea by decades. In the 1950s, the French-American astronomer Gérard de Vaucouleurs proposed what he called the local supercluster, a flattened concentration of galaxies centered on the Virgo Cluster, noticing that galaxies across a broad region of sky, including our own, seem to share a rough concentration toward Virgo. That earlier picture, built entirely from galaxy positions and counts, the tools available at the time captured something real. What it could not do, because the velocity measurements required simply did not exist yet, was settle the actual boundary of the region, or determine whether the whole area was one coherent basin or several overlapping ones. That is exactly the gap Tully's velocity-based method would close decades later, replacing a count-based guess with a measured boundary. It was through that fog that astronomers first noticed something pulling. In the 1980s, a group of 7 researchers, sometimes nicknamed the Seven Samurai, were measuring how fast a set of distant galaxies were moving away from us. By that point in the 20th century, the general rule was well established. The universe is expanding, so almost everything should be receding, and the farther away a galaxy is, the faster it should appear to recede. But when the Seven Samurai compared their measurements to that expectation, a large group of galaxies was moving slightly differently, as if something with enormous mass, sitting behind the dust of the zone of avoidance, were tugging the whole region sideways, off the smooth expansion everyone expected. They called it the Great Attractor, because at the time, that is all they could honestly say about it. Something attracting. Somewhere great. The name was a placeholder. Admittedly so, and it stayed that way for longer than anyone expected, because confirming what actually sat behind that curtain of dust turned out to be one of the more stubborn problems in 20th century observational astronomy. Ordinary visible light is exactly the wrong tool for looking through a galaxy's own disk. Starlight and interstellar dust scatter and absorb it so effectively that entire galaxies, sitting directly behind the Milky Way from our point of view, simply do not show up in an ordinary photograph, however long the exposure runs. What eventually broke the problem open were wavelength dust, is far less effective at blocking. Infrared light, which passes through cosmic dust far more easily than visible light does, and radio waves, particularly the specific radio signal emitted by clouds of neutral hydrogen gas, the raw material galaxies are built from, which travels through dust almost as if it were not there at all. Surveys built specifically to look in those wavelengths, patiently scanning the zone of avoidance through the 1990s and into the 2000s, began filling in galaxies that had been sitting there the entire time, simply unseen, thousands of them, eventually charted in a region of sky that earlier catalogues had left almost entirely blank. What that patient infilling confirmed, piece by piece, was that the pull the Seven Samurai had measured was not a mistake, an artifact of some unaccounted-for calibration error or a trick of streaming gas rather than galaxies. It was ordinary matter, doing what matter does under gravity, in a location that happened to be difficult for us, specifically to see, simply because of where our own galaxy sits relative to it. A civilization on a planet 100,000 light-years farther around the Milky Way's disk, looking outward from a different angle, would have had a perfectly clear view of it from the start, and no zone of avoidance to speak of at all. The blind spot was never a property of the Great Attractor. It was a property of the particular window we happened to be looking through. That difficulty says something worth sitting with for a moment. The map of the universe has a permanent blind spot, stitched from wherever the observer happens to be standing, and every civilization anywhere in the cosmos would have a blind spot of its own, in a different direction, hiding a different part of the sky. It is not a flaw in the instruments. It is what it costs to live inside a galaxy instead of floating somewhere outside it. There is a modest comfort tucked inside that limitation, easy to miss on a first pass. The zone of avoidance is not evidence of anything hidden from us on purpose, and it is not evidence that the universe treats any single vantage point as special. It is the ordinary, unavoidable cost of viewing a three-dimensional sky from a fixed position inside one of its own galaxies. The same cost any observer anywhere would pay from wherever their own galaxy happened to place them. The universe is not keeping a secret. It is simply large, and we are simply somewhere specific inside it. The way anyone standing in a forest has trees blocking part of the view, however carefully they turn. When Tully's team built the full velocity map that produced Laniakea, the Great Attractor did not vanish into a footnote. It turned out to sit almost exactly at the gravitational center of the whole basin. The low point in the landscape all the surrounding galaxies, including our own, are gently sliding toward. The Milky Way is not near that center. We sit out toward the edge of Laniakea, closer to the boundary with a neighboring basin called Perseus-Pisces than to the Great Attractor itself, moving toward the center of our own basin at a modest, well-measured pace, the way a leaf near the rim of a slow whirlpool still drifts. Eventually, toward the middle, the independent distance measurement doing the real work here deserves a name, because it is not a minor detail. It is the reason any of this could be checked at all. In the 1970s, Tully himself, working with the astronomer J. Richard Fisher, had shown that a spiral galaxy's rotation speed, how fast its stars swing around its center, correlates closely with its true brightness. Faster spinning spiral galaxies are reliably more luminous ones. Measure how fast a galaxy is spinning, a quantity read directly off its own light with no reference to redshift at all, and its true brightness can be estimated. Compare that true brightness to how bright the galaxy actually appears from Earth, dimmed by distance the way any light source dims with range, and a distance falls out of the comparison, entirely independent of the galaxy's redshift. It is that independence that makes the whole method work. Redshift alone always blends real motion together with the expansion of space, and only a second, separate distance measurement built from something other than redshift can pull the two apart again. None of this motion is something you could feel, any more than you can feel the Earth's rotation while sitting still in a chair, but it is not hypothetical. Astronomers measure it the same way they measure any other velocity in astronomy, by comparing a galaxy's redshift, which records how fast it is being carried by the expansion of space, against its distance measured independently through other means. The brightness of certain stars, the size of certain features, methods checked against each other and refined for decades. When the redshift implies more speed than the distance can explain, or less, the leftover is real motion. And that leftover motion is what draws the shape of the basin. It is worth being clear about how the Great Attractor and Laniakea's own name relate to each other, since both are sometimes used a little loosely in casual conversation. The Great Attractor is a location, a specific, massive concentration of galaxies, the deepest point in the local gravitational landscape. Laniakea is the basin itself, the entire, much larger region of space whose galaxies all drift toward that one deep point. A useful, if imperfect, comparison is the difference between a specific city sitting at the mouth of a river and the entire watershed draining toward it. The watershed is a whole region defined by where its water is headed, and confusing the two loses exactly the distinction that made Tully's mapping method worth inventing in the first place. So, the picture sharpens. Laniakea is not a wall, not a sphere, not a shape with a clean outline the way a country has a border on a map. It is a set of directions converging. The way every gutter on a hillside eventually agrees about which way is down. The Great Attractor marks the deepest part of that convergence in our neighborhood. The way the lowest point of a watershed marks where every stream in it is, in the end, heading. Standing inside Laniakea, near its edge, the Milky Way is one galaxy among roughly 100,000 large ones. Caught in the same slow slide, none of them tied to any of the others by a bond that will outlast the pattern itself. That word slide is doing important work, and it is worth being precise about what it is not. It is not falling in the dramatic sense of something plunging toward a center and picking up speed the way a stone falls toward the ground. Every galaxy inside Laniakea is still, first and foremost, carried outward by the expansion of space, the same way every galaxy everywhere is. The Great Attractor's pull is a small correction riding on top of that much larger outward motion, enough to bend the path, enough to define a direction, not enough to overcome billions of years of cosmic expansion and pull the whole basin into one merged object. That is exactly why Laniakea counts as a pattern rather than a system. The pull is real, and it organizes the traffic, but it never wins outright. There is a further consequence of that arrangement worth sitting with, because it says something about how ordinary our own vantage point actually is. The Milky Way is not privileged inside Laniakea in any way. It is not near the center, not unusually massive compared to the basin's largest members, and not treated any differently by the mathematics of the velocity field than any other galaxy caught in the same drift. Being near the edge, close to a neighboring basin, is not a demotion either. Every basin has an edge somewhere, and every galaxy inside one sits at some particular distance from its own center. The way every point in a country sits some particular distance from its capital. Ordinary placement was always the most likely outcome for any galaxy anywhere, and the Milky Way's position confirms that expectation rather than breaking it. It is worth returning once more to the ordinary case from the start of the night, because the contrast is the whole point. Inside the local group, gravity has already won. The pull between the Milky Way and Andromeda is strong enough, at that short range, to overpower expansion completely, which is why the two galaxies are moving toward each other rather than apart on a path that ends in a merger. Inside Laniakea, at 100 times the distance, gravity has not won and will not win. The Great Attractor can bend a path. It cannot close one. The difference between those two outcomes, bent versus closed, is the difference between a pattern and an object, and it is set entirely by distance, mass, and time, not by how impressive the structure looks on a map. To understand why patterns like Laniakea exist at all, and why there are larger ones still, it helps to go back much further than any galaxy, back to a universe that was still almost, but not quite, perfectly smooth. The oldest light astronomers can observe is the cosmic microwave background, a faint glow left over from a time when the universe was about 380,000 years old, hot and dense enough that light could not yet travel freely through it. When that light was finally released, it carried a snapshot of how matter was arranged at that moment. The remarkable thing about that snapshot is how even it is. The temperature of that ancient light is the same in every direction to within about 1 part in 100,000. Missions built specifically to measure it. First, COB in the early 1990s, then WMAP through the 2000s, then Planck in the 2010 seconds, each more sensitive than the last, kept confirming the same striking near uniformity, mapping the sky's temperature more and more finely without ever finding a hidden large-scale asymmetry underneath it. Almost nowhere is there any texture at all. Almost. Those tiny variations, 1 part in 100,000, are not noise, and they are not arbitrary either. The leading explanation for where they came from reaches back to the universe's very first fraction of a second, to a brief, extraordinarily rapid stretch of expansion called inflation, during which unimaginably small quantum fluctuations, the same restless jitter that shows up in any sufficiently small, sufficiently sensitive physical system, were stretched, almost instantly, up to sizes that would eventually span galaxies. It is a strange thing to sit with. The largest patterns astronomers will map tonight may trace their outline back to the smallest, most fleeting kind of randomness physics knows about, magnified before the universe was even a fraction of a second old, then left largely alone to grow, slowly and patiently, for the 13.8 billion years since. They are the seeds of everything that came after. Every galaxy, every cluster, every basin like Laniakea, and everything larger still. A region that started out just barely denser than average had, from the very beginning, a very slight gravitational advantage. It pulled in slightly more matter than its surroundings, which made it slightly denser still, which let it pull in even more. Over billions of years, that small, patient advantage, repeated across a universe full of tiny variations, is what turned an almost featureless fog of gas into the galaxies, clusters, and larger patterns astronomers now map. What that growth produces is not scattered at random. Gravity does not build isolated islands in a uniform sea, because the initial variations were themselves connected. Denser regions tended to sit near other denser regions, rather than being placed independently by chance. The structure that grew out of them kept that connectedness, and it grew into a shape with a name, the cosmic web. It is worth being clear about scale before the geometry gets described further. So the words filament and node do not sound smaller than they are. A single filament in the cosmic web can stretch for hundreds of millions of light years, threading between clusters that are themselves each home to thousands of galaxies. These are not delicate threads in any ordinary sense of the word. They are simply thin, only by comparison to the even larger nodes and sheets they connect. Matter collects most densely at the nodes, the crossing points, which is where the richest galaxy clusters tend to sit. It threads between those nodes along filaments, long, relatively thin bridges of galaxies and gas. It also gathers into broader sheets, sometimes called walls, and it thins out almost completely inside voids. Enormous, roughly spherical regions, tens or hundreds of millions of light years across, where galaxies are sparse and the space between them is close to empty. One of the first voids ever mapped in real detail, in 1981, sits in the direction of the constellation Boötes, roughly 250 million light-years away, and stretches across something on the order of 300 million light-years itself. A volume so empty of catalogued galaxies that early radio astronomers half joked they could have fit the entire local group inside it several thousand times over and still had room left. It is not truly empty. A handful of galaxies do sit scattered through it, more than early, sparser surveys initially found, but the contrast with an ordinary, galaxy-rich region of the cosmic web is stark enough that the void needed its own name and its own careful mapping the negative space of the same process that builds filaments and nodes. Matter drawn toward the denser regions nearby, leaving the space behind it thinner than it started. It helps to picture why gravity, left alone with a slightly uneven starting fog, would ever settle into threads and sheets, rather than into neat, evenly spaced spheres. A perfectly round clump would only form if the surrounding density were perfectly even in every direction, which the early universe's texture never quite was. Some directions around any given overdense patch were always a little denser than others, simply by chance, in the original 1 part in 100,000 pattern. As that patch collapsed under its own gravity, it collapsed fastest along whichever direction had the least resistance, flattening first into a sheet rather than a sphere, the way a lump of dough flattens under a rolling pin more than it compresses into a ball. Sheets that collapsed further, along their own thinnest direction, flattened again into filaments, and filaments that kept collapsing along their length gathered, at their crossing points, into the dense nodes where the richest clusters now sit. None of that shape was designed. It is the geometry gravity produces automatically when it is left to amplify small variations for a long enough time in 3 dimensions without anything to stop it. The same rule that draws water toward the lowest point of a landscape draws matter toward the densest point of the early universe's texture. And because that texture was made of connected patches rather than independent dots, the result looks like a web rather than a field of separate blobs. For a long time, this shape was mostly theoretical, sketched out through careful mathematics decades before there was any way to check it directly against the real sky. An early version of the idea, sometimes called pancake theory, was worked out by the Soviet physicist Yakov Zeldovich around 1970, describing how an almost uniform cloud of matter, collapsing gently under its own gravity, would tend to flatten first into broad sheets, rather than clumping straight into isolated blobs. It was a reasonable mathematical guess, built well before any survey existed that could have confirmed or denied it. The confirmation came slowly, 1 patient survey at a time. Through the 1980s and 1990s, teams of astronomers took on the tedious work of measuring redshifts, not for a handful of galaxies, but for thousands of them, one at a time, gradually filling in a genuine 3-dimensional map of the nearby universe, rather than the flat, 2-dimensional map a simple photograph provides. As each survey grew larger, the pattern Zeldovich's mathematics had predicted kept appearing in the data. Galaxies were not scattered randomly, and they were not simply clumped into isolated islands either. They sat along sheets and threads, with wide, nearly empty regions in between, exactly the geometry the old pancake calculations had anticipated, now filled in with real coordinates instead of equations. Once computers grew powerful enough, the same growth could be run forward directly, rather than only inferred from a snapshot of the present-day sky. A simulation can be seeded with a version of the early universe's own gentle texture, the same 1 part in 100,000 variations recorded in the cosmic microwave background and then simply left to evolve under gravity, 1 calculated time step after another, for the equivalent of 13.8 billion simulated years. One of the most influential of these efforts, the Millennium simulation, completed in 2005, tracked more than 10 billion individual particles of matter across a simulated volume over 2 billion light-years on a side, updating each particle's position under the combined gravity of all the others again and again until the near-smooth starting texture had grown into a detailed, 3-dimensional web, dense nodes where filaments crossed, threading strands connecting them, and broad, nearly empty voids in between, structurally indistinguishable. In its overall geometry, from the web, astronomers were independently mapping with real telescopes at the same time. 2 completely different methods, one built from calculation and one built from observation, arrived at the same shape. Once the web's full geometry was mapped, a slightly unsettling accounting became possible. How much of the universe's volume actually sits inside voids, as opposed to the denser filaments, sheets, and nodes? The answer, from later, more detailed surveys, is that voids account for a clear majority of the volume of the universe, even though they contain only a modest minority of its galaxies. Most of the room, in other words, is nearly empty. Most of the galaxies are crowded into a comparatively thin, connected skeleton threading through that room. Earth and the Milky Way and Laniakea itself all happen to sit on that skeleton rather than adrift in one of the great empty rooms, which is worth remembering the next time an empty night sky looks, from here, unusually full. This is the machinery behind every pattern described tonight, including Laniakea and including whatever comes next. A basin of attraction like Laniakea is, in effect, a piece of that web, seen from the inside, at the resolution of individual galaxy flows rather than galaxy positions. The Great Attractor is a locally dense node in the web, close enough and massive enough to bend the paths of everything nearby, and the very largest patterns astronomers have tried to name, the ones tonight is building toward, are simply larger stretches of the same web, filaments and walls extended far enough and mapped at a scale ambitious enough to earn a headline calling them the biggest structure in the universe. It is worth being honest about a limit here too. The cosmic web is not infinite in its texture. On small scales, it is intricate, rich clusters, threading filaments, careful contours, but that intricacy has to run out somewhere, because the fluctuations it grew from were themselves small and limited in scale, and because gravity has only had 13.8 billion years to work with, somewhere above the scale of the very largest superclusters, the web should, in principle, stop looking like a web at all, and start looking like something else entirely. A smooth, textureless fog, the same in every direction, no matter where you happen to be standing inside it. Whether that expectation actually holds, once astronomers try to map it directly, is where tonight turns next. Modern cosmology is built on a simple working assumption, one so basic it is usually called, without much ceremony, the cosmological principle. On a large enough scale, the universe looks roughly the same everywhere, and roughly the same in every direction. No location is special, no direction is favored. It is not a claim that nothing varies. Clearly, galaxies clump, and filaments thread, and voids sit empty. It is worth being clear that this principle is not something cosmologists arrived at reluctantly or adopted only because the mathematics happen to be simpler that way. It follows from a much older, much broader piece of scientific reasoning, sometimes called the Copernican principle, extended over centuries from a single stubborn insight about Earth not sitting at the center of the solar system, that no observer's location deserves to be treated as automatically special without solid evidence forcing that conclusion. Applied to the larger scales, that same caution becomes the cosmological principle, and it has earned its keep the same way the original insight did, by being tested directly rather than simply trusted. For a long time, that scale was mostly assumed rather than measured. It had to be true eventually, in principle, for the standard picture of the universe's expansion to keep working the way it does. But eventually is not a number, and astronomers like numbers they can check. Large galaxy surveys, built specifically to map redshifts across enormous volumes, gave them a way to test it directly. Draw a large enough box anywhere in the observed universe, count how much matter is inside it. Then draw an equally large box somewhere else, and count again. If the totals keep coming out close to each other, no matter where the boxes are placed, the universe is behaving the way the cosmological principle says it should, at that size. That test needed a particular kind of survey to run properly. One wide enough and deep enough to contain many separate boxes the size in question. Not just one or two. The two surveys that finally made the test possible arrived within a few years of each other. The 2-degree field galaxy redshift survey, completed in the early 2000s, measured redshifts for roughly 200,000 galaxies. The Sloan Digital Sky Survey, the same project that later produced the Sloan Great Wall, eventually measured redshifts for well over 1 million. Both were, for the first time, large enough to be sliced into many independent volumes and compared against each other directly. Rather than simply describing the one patch of sky each earlier, smaller survey happened to cover. The answer, once surveys were large enough to ask the question properly, was that homogeneity does arrive, and it arrives at a scale that can be pinned down, roughly a few 100 million light-years. Draw a box smaller than that, almost anywhere, and you might land inside a rich cluster or deep inside a void, and the count will look nothing like the universal average. Draw a box that size or larger, and the differences between one box and another shrink down toward nothing. Put a little more precisely, cosmologists describe this using something close to a fractal measurement, tracking how the average density found inside a sample box changes as the box grows larger. On small scales, the count is genuinely fractal-like, clumpy and uneven no matter how the box is shifted around, because the cosmic web's filaments and voids dominate at that size. As the box grows past the homogeneity scale, that fractal behavior gives way, cleanly, to an ordinary, boring average that barely moves no matter where the box is placed next. The transition is not vague or approximate. Large surveys can plot it directly, watching the fractal-like scatter narrow, box size by box size, until it effectively vanishes. The texture of the cosmic web, filaments and voids and all, is real, and it is dramatic on the scales where galaxies and clusters live. But it is not infinite in reach. Past the homogeneity scale, the universe stops behaving like a web and starts behaving like a fog, evenly spread, however you slice it. This is where the trouble starts for the phrase biggest structure. If the universe is close to uniform on scales beyond a few 100 million light-years, then anything claimed to be a coherent structure larger than that is, almost by definition, sitting right at the edge of what the universe's own statistics will support. It is not that nothing that large can be found. Density does still vary a little, even past the homogeneity scale. A genuinely rare, genuinely large overdensity can exist. The way an unusually tall wave can still occur in an ocean that is, on average, calm. The trouble is telling that rare wave apart from an illusion made by the method used to look for it. There is an old, almost playful way of describing this same trap that predates modern cosmology by a long way: the constellations. Every named constellation in the night sky, a hunter, a bear, a set of scales, is a genuine pattern in the sense that the stars really do sit where the outline says they sit. None of them is a genuine structure in the physical sense. The stars making up a constellation are often nowhere near each other in 3 dimensions, sitting at wildly different distances along roughly the same line of sight, with no gravitational connection between them at all. The shape exists entirely because of where Earth happens to be standing, and because the human eye is extremely good at finding outlines in scattered points. Whether or not those points have anything real in common, large-scale structure surveys run exactly the same risk, at a scale too vast for the eye to trace directly, which is why they use an algorithm instead. The algorithm is more careful than an eye, but it is not immune to the same basic trap. Given enough scattered points and a generous enough rule for connecting them, it too will trace a bear into the noise, given the chance. Here is the part that matters most for how these claims get made and get disputed. Astronomers do not usually stumble across a structure by eye. They search for it algorithmically, choosing a tracer, some population of objects easy to catalogue across a large volume, then running a mathematical rule that groups nearby tracers into a single claimed structure whenever they sit closer together, on some chosen measure than a set threshold. That rule will always return a group, even inside genuinely random data, with no real structure at all. A search of that kind, sometimes called friend-of-friend linking, will connect together some tracers purely by chance because in any large enough set of points scattered through space, some of them will happen to cluster a little, whether or not anything physical ties them together. There is a second, quieter reason large-scale homogeneity mattered enough to chase down directly, beyond keeping Hubble's law tidy. Precision cosmology, the whole modern effort to pin down the universe's age, its composition, and its expansion history to several decimal places, depends on treating the observable universe as a fair, representative sample of the universe as a whole. Every constraint on dark energy, every measurement of how much of the universe is ordinary matter versus dark matter assumes that the volume being measured is large enough to average out local flukes, rather than accidentally sampling an unusually dense or unusually empty patch. Confirming the homogeneity scale directly, rather than simply hoping it held, was less a curiosity and more a foundation check for an entire discipline's confidence in its own numbers. It is worth pausing on why cosmologists were so invested in checking this in the first place, rather than simply assuming it and moving on. The entire practice of describing the universe's expansion with a single number, the way Hubble's law relates distance and recession speed with one consistent rate, only makes sense if that rate really is close to the same everywhere. Once measured over a large enough volume, if the universe stayed lumpy and uneven at every scale, with no size at which the differences finally washed out, there would be no single expansion rate to speak of at all, only a patchwork of locally different ones, and a great deal of modern cosmology would need to be rebuilt from a very different starting assumption. The homogeneity scale is not a footnote to that larger project. It is one of the load-bearing checks underneath it. That does not make every claimed large structure fake. It means each one needs the same two questions asked of it, carefully, before the headline is trusted. Is the overdensity itself statistically significant, more than could be expected from ordinary chance in a survey that size? And is the grouping algorithm's threshold doing real physical work, or is it simply drawing a generous line around whatever traces happen to be nearby? Both tests take real, patient work to run properly, which is part of why these disputes can take years to settle rather than minutes. Statistical significance has to be checked against realistic simulations of what a random, structureless catalogue the same size would produce, run many times over, not just a single rough estimate. And the algorithm's own threshold has to be tested against multiple reasonable choices, not just the one that happened to produce the most striking headline. Structures that pass both tests, carefully run, earn their size. Structures that only pass the first, or neither, are closer to shapes seen in noise. Real data, real coordinates, and a boundary that exists mostly because of where the line was drawn. It is worth noticing, in advance, roughly where the record holders still ahead tonight sit relative to that homogeneity scale, because the comparison does most of the explaining on its own. A structure a few 100 million light-years long sits close to the boundary itself, in the range where a genuine, statistically ordinary overdensity can still occur without breaking anything about the cosmological principle. A structure a few billion light-years long sits well past it, in territory the standard picture says should already be smooth, and a structure claimed at 10 billion light-years sits so far past it that its very existence, if fully confirmed, would be one of the more surprising results in modern cosmology, not because the physics behind gravity or the cosmic web would need to change, but because a chance fluctuation that large, this early in cosmic history, would be genuinely difficult to explain within the standard model astronomers currently rely on. Keep that distinction in mind. The next stretch of tonight walks through the actual record holders, the specific structures that, at one point or another, carried the headline "the biggest structure in the universe," and not one of them passes through that distinction unscathed in quite the same way twice. The first structure to earn the biggest ever headline, in the modern sense, came out of a survey that today sounds almost quaint in scale. Through the 1980s, the astronomers Margaret Geller and John Huchra working at the Harvard-Smithsonian Center for Astrophysics, set out to measure redshifts for thousands of galaxies in a strip of the northern sky, patiently building one of the first genuine three-dimensional maps of the local universe. When they plotted the results, a shape emerged that had not been anticipated in that much detail. A broad, flattened sheet of galaxies, roughly 500 million light-years long, only a few 100 million light-years across, and comparatively thin, like a wall standing on its edge. The technique itself was almost stubbornly simple. Geller and Hutra pointed their instrument at a narrow strip of sky, measured a redshift for every galaxy bright enough to catch inside it, one after another, then plotted each galaxy's position as a single point, placed at an angle across the sky and at a distance implied by its redshift. Do that for one galaxy and the plot means nothing. Do it for several thousand, across a long, thin slice of the sky, and a shape can emerge on its own, with no assumption built in about what that shape ought to look like. When Geller and Hutra finished their slice, the shape that emerged was not a scattering of dots. It was a wall, thin and broad, stretching across the entire width of their survey, so much longer than it was wide that some of their own early plots simply ran out of room to draw the whole thing on one page. They published it in 1989, called it, without much hesitation, the Great Wall, and for a while, it stood as the largest coherent structure anyone had mapped. It held that record for over a decade, not because searching had stopped, but because deeper three-dimensional surveys of that quality were slow and expensive to build. That changed with the Sloan Digital Sky Survey, an ambitious project that measured redshifts for hundreds of thousands of galaxies across a much larger volume of sky than Geller and Hutra had access to. The instrument behind it, a dedicated 2.5-meter telescope at Apache Point Observatory in New Mexico, was purpose-built to do exactly the kind of patient, repetitive cataloguing that finding a structure like this requires. Not a single dramatic image, but redshift after redshift, galaxy after galaxy, accumulated over years until the sample was large enough for a shape spanning more than 1 billion light-years to become visible in the data at all. In 2005, a team led by the astronomer Richard Gott published the results in a paper called Identifying an Even Larger Sheet Than Geller and Hutra's Original, promptly named the Sloan Great Wall, roughly 1.4 billion light-years long, several times the length of the wall it succeeded. For a few years, that number carried the headline. There is a small, almost tender detail in how Geller and Hutra chose to present their original 1989 map, worth carrying forward into everything that follows. Rather than publishing only coordinates and numbers, they released a now well-known diagram, nicknamed by other astronomers the Stick Man, in which the outline of the CfA2 slice happens to trace a shape that looks, if you squint, a little like a figure with arms raised. Astronomers have pointed to it for decades since, as an accidental, almost affectionate reminder of exactly the caution Chapter 4 spends its time on. The eye, and even a rigorously plotted survey, will find a recognizable shape in scattered points, whether or not that shape means anything on its own. The Great Wall itself was not an accident of pattern matching. It held up under every later, larger survey that checked it. The stick man in the corner of the same plot was. It is worth noticing what stayed the same across that jump from one wall to the next, larger one. The method did not change. The kind of object being described did not change. What changed was simply the size of the survey doing the looking. A larger, deeper catalogue of galaxy redshifts will, almost automatically, tend to reveal a larger version of the same kind of pattern, the way a wider window reveals more of a landscape without the landscape itself growing any bigger. That pattern would repeat, more dramatically, in the structures still ahead tonight. There is a particular kind of care both discovery teams took that is easy to skim past, and worth naming directly, because it will matter again before tonight is over. Neither the CfA2 Great Wall nor the Sloan Great Wall was found by an algorithm hunting specifically for the largest possible shape. Both emerged from a plain, deliberately unbiased redshift survey, a project simply cataloguing every galaxy bright enough to measure across a defined patch of sky, with no threshold tuned in advance to produce an impressive result. The wall shape showed up in the finished map on its own, which is a meaningfully different kind of discovery than actively searching a catalogue for the largest linkable group a chosen algorithm can assemble. That difference in method is exactly what later candidates, built from sparser, more distant traces and more aggressive linking rules, would not always be able to claim. Notice what both of these structures actually are, physically, before the next candidates arrive. They are overdensities. Real, measured concentrations of galaxies, sitting where the cosmic web's nodes and filaments happen to line up along roughly the same sheet when viewed from Earth's particular vantage point. Neither one is remotely close to being gravitationally bound. The Sloan Great Wall spans more than 1 billion light-years. Even at the very generous end of estimates for how much mass sits along its length, nothing that extended has had anywhere near enough time or enough concentrated pull to draw its own far ends together into one system. Both walls are patterns in the web, mapped with real data and real statistical care, carrying names that make them sound like single objects because English is not built for any gentler way to say it. That distinction did not stop the search for something bigger, and by the early 2010 seconds, a new kind of candidate had entered the conversation, built not from ordinary galaxies but from quasars, extremely luminous, extremely distant objects bright enough to be seen and catalogued across a much larger volume of the universe than an ordinary galaxy survey can reach. Quasars themselves are worth pausing on briefly, since they play the same tracer role gamma-ray bursts will take over in the next chapter, at a slightly smaller distance. A quasar is an extraordinarily bright, compact source of light and radio emission, powered by a supermassive black hole actively feeding on surrounding gas at the center of a distant galaxy. The process releases so much energy that the quasar itself can far outshine every star in its host galaxy combined, visible across a much larger volume of the universe than the comparatively faint galaxy hosting it. That brightness is precisely what makes quasars useful for exactly the ambitious kind of survey Clowes and his colleagues were running. In 2013, the astronomer Roger Clowes and colleagues, working from a large quasar catalogue, identified a grouping of 73 quasars, spread across a truly enormous span, roughly 4 billion light-years at its widest, more than 3 times the length of the Sloan Great Wall. They called it the Huge Large Quasar Group, or Huge-LQG, and were careful, in the paper itself, to flag exactly the tension tonight has been building toward, a structure that size sits well past the homogeneity scale that the standard cosmological model expects the universe to smooth out by, which meant either the model needed a second look or the structure itself needed one. It got one. Within the same year, the astronomer Seshadri Nadathur published a direct methodological challenge, arguing that a grouping algorithm run on quasar positions, using a generously large linking threshold, will readily assemble large, wall-like shapes purely from statistical noise, and that simulated, genuinely random quasar catalogues containing no real large-scale structure at all produce similarly sized false groupings when searched the same way. The dispute was never really about whether Clowes and colleagues had made an error in counting. It was about whether the word structure, applied to a set of quasars sharing a generous linking radius, meant the same thing as a genuine, physically connected overdensity, or whether it meant something closer to a shape a person can trace through scattered dots if the dots are numerous enough and the pen is allowed to wander far enough between them. Both readings can be true about the same catalogue at once, which is the uncomfortable, honest place this leaves things. The Huge-LQG's quasars are real, their positions are measured, and the region does appear to hold somewhat more of them than an average patch of sky its size. Whether that mild excess deserves to be called one structure, spanning 4 billion light-years, or whether it is better described as an unremarkable statistical fluctuation traced generously by an algorithm built to find exactly that kind of shape, has never been fully settled. It is the first entry on tonight's list that comes with an asterisk attached at the moment of its own announcement. And it would not be the last. A related quasar and gamma-ray burst catalogue would later turn up a second, similarly disputed claim. A giant ring-shaped arrangement of bursts, roughly 5 billion light-years across, announced by a partly overlapping group of researchers at a comparable distance to the record holder still ahead tonight. It drew the identical methodological question the moment it was published. A genuinely rare, physically meaningful alignment, or a shape a sparse, unevenly sampled catalogue was always somewhat likely to produce somewhere, given a large enough search and a generous enough eye for rings and walls traced through scattered points. Astronomers have not reached a full consensus on that one either. By this point in the night, the pattern should feel familiar rather than alarming. At the very largest scales, close to and beyond the homogeneity limit, almost every ambitious claim arrives with the same open question attached, and living with that open question honestly is simply part of how this branch of astronomy works. The current holder of the biggest structure headline was not found with galaxies or quasars at all, but with the most violent, briefest events astronomers know how to catalogue: gamma-ray bursts, sudden, extraordinarily energetic flashes thought to mark the collapse of certain massive, dying stars or the collision of extremely dense stellar remnants. A single gamma-ray burst can, for a few seconds, outshine an entire galaxy, which makes it visible across a large fraction of the observable universe. Useful, in principle, as a tracer for mapping matter at distances ordinary galaxy surveys cannot easily reach. Ordinary galaxies, even bright ones, fade below the reach of most surveys well before they approach the true edge of the observable universe. Gamma-ray bursts do not have that limitation, at least not nearly as severely. Their extreme brightness means a handful of instruments, watching the whole sky for exactly this kind of sudden flash, can catch bursts from galaxies far too faint and far too distant for their host galaxy to ever be catalogued directly on its own. That is the appeal of using them as tracers for the largest scales. Not that they are more numerous than galaxies, they are far rarer, but that the ones astronomers do catch can come from much farther away, filling in a volume of the universe ordinary surveys simply cannot reach with anywhere near the same completeness. Gamma-ray bursts themselves were, for a surprisingly long stretch of the 20th century, a genuine mystery rather than a mapping tool. They were first noticed by accident in the late 1960s, by American satellites designed to watch for the gamma-ray signature of nuclear weapons tests, which instead kept registering sudden flashes coming from deep space rather than from Earth. It took decades of further observation, and eventually satellites purpose-built to catch the faint afterglow that follows the initial flash, to establish that these events were coming from far outside our own galaxy, tied to the most extreme deaths and collisions massive stars and dense stellar remnants are capable of. Only once that distance scale was firmly established could anyone consider using them as tracers for mapping matter at the very largest scales. Exactly the role they play in this chapter. In 2013 and 2014, the astronomers Istvan Horvath, John Hakila, and Zsolt Bagoli plotted the sky positions of several hundred gamma-ray bursts and noticed a cluster of them sitting closer together on the sky and in distance than random chance would predict, spread across the constellations Hercules and Corona Borealis. They named the result the Hercules-Corona Borealis Great Wall, and its claimed extent dwarfed everything that came before it, on the order of 10 billion light-years across, roughly a tenth the diameter of the entire observable universe, which is itself only about 93 billion light-years wide. By that measure, it remains, as of this recording, the largest structure ever proposed. 93 billion light-years is itself a number worth pausing on before moving further, because it can sound like a contradiction of something said earlier tonight. The universe is 13.8 billion years old. And yet the observable universe, the volume containing everything whose light could in principle have reached us by now, is described as 93 billion light-years across, not 27.6. The difference is entirely due to the expansion of space itself. A photon that set out toward us 13.8 billion years ago was emitted by a source that has, in the meantime, continued to be carried farther away by that expansion. So the present-day distance to that source is considerably larger than the distance light alone would suggest. It is a genuinely counterintuitive result, and one cosmologists have had to explain patiently and repeatedly, precisely because ordinary intuition about travel time and distance, built entirely from experiences on Earth, was never designed to handle a universe whose own fabric is stretching while the light crosses it. It is worth sitting, deliberately, with how strange that number is, because the earlier chapters of tonight were not decoration. A region 10 billion light-years across is larger than the distance light has had time to travel, in any direction, since the universe began 13.8 billion years ago. Once the effects of cosmic expansion on that travel are properly accounted for, no signal, gravitational or otherwise, has ever connected one end of a region that size to the other. It helps to put that 10 billion light-year figure directly beside the Sloan Great Wall's 1.4 billion, since the jump between the two record holders is itself larger than the gap between the very first Great Wall and the Sloan Great Wall that succeeded it. Each new record has not simply nudged the previous one, it has multiplied it several times over, a pattern that says as much about how much deeper each successive survey could see as it does about the universe itself, echoing exactly what Chapter 5 noted about the CfA2 wall, giving way to the Sloan wall, a wider window, not a larger landscape. Whatever the Hercules-Corona Borealis Great Wall turns out to be, physically, it was never a candidate for a bound object, not even in principle, not even given the entire age of the universe to work with. Its own discoverers never claimed otherwise. The paper describes an excess in the distribution of traces, not a body held together by gravity. The more contested question is the one Chapter 4 raised. Is the excess itself real, or is it the kind of shape a linking algorithm draws generously through noise? It is worth being specific about what that kind of algorithm actually does, since the same basic method produced both the Huge-LQG and the Hercules-Corona Borealis Great Wall. A researcher chooses a maximum separation, a linking length, and connects any two traces closer together than that distance into the same group. Any tracer linked, even indirectly, through a chain of such connections, joins the same structure, however sprawling the resulting shape turns out to be. Choose a short linking length, and only the tightest, most obviously real concentrations survive. Choose a longer one, and the algorithm becomes far more willing to stitch together traces that are merely coincidentally nearby, chaining them into a single named structure that may have no more physical unity than a scattering of gravel happens to have, just because a generous enough ruler was used to connect the pieces. Gamma-ray bursts are rare. Their distances are harder to pin down precisely than a nearby galaxy's, and a few hundred events spread across the entire observable universe is a comparatively small sample to search for patterns in. Follow-up analyses have not reached a settled consensus. It helps to be specific about what confidence actually measures here, since the phrase gets used loosely elsewhere. A statistical test of this kind estimates how often a clustering this strong would turn up by pure chance in a universe with no real structure at that scale at all, if the same search were run over and over on random data. A result found in only one run out of 100 is more convincing than one found in one run out of 5. But neither, on its own, proves the structure is real. Both simply describe how surprised a careful statistician should be, which is a different, more honest question than a headline usually has room for. Some statistical tests of the original claim found the clustering unlikely to be chance at a modest level of confidence. Others, testing the same or similar gamma-ray burst catalogues with different assumptions about burst distances and different clustering statistics, closer to the kind of coincidence that turns up somewhere in almost any catalogue that size purely by chance. As of this recording, no independent survey using a different, more numerous tracer has confirmed an overdensity of comparable size in the same patch of sky, which is the kind of confirmation a claim this large would need before most astronomers would treat it as settled. A particular kind of scientific humility sits inside how this dispute has actually played out, and it is worth naming plainly, because it distinguishes an honest disagreement from a manufactured one. Horvath, Hakila, and Bagoli published their result in a peer-reviewed journal with their methods, their catalogue, and their statistics laid out clearly enough that other astronomers could check the claim directly, which is exactly what happened next. Independent groups revisited the same or similar data, applied different assumptions, and reported different confidence levels, sometimes lower than the original announcement, without anyone accusing anyone else of fraud, exaggeration for its own sake, or bad faith. That is what a genuinely open scientific question looks like from the inside, as opposed to a settled fact still being argued about for other reasons. It moves slowly, through publication and reply, rather than through certainty declared once and left unchallenged. So the honest answer to the biggest structure question, at the record holder level, is not a clean one, and it would be dishonest to pretend otherwise for the sake of a tidier telling. The Hercules-Corona Borealis Great Wall is a real, published, still-cited claim built from real gamma-ray burst positions. It may represent a genuine, rare overdensity, the kind Chapter 4 allowed for, an unusually tall wave in an otherwise calm sea. It may also turn out, on further data, to be closer to the Huge-LQG's fate, a shape assembled generously from a modest, real signal buried in a small sample, more a property of the search method than of the universe. There is a useful comparison to keep close by while that question stays open. Astronomers do not treat a disputed claim as something to be embarrassed about or quietly dropped from the record. The published, peer-reviewed announcement stays part of the scientific conversation, cited, tested, and refined by exactly the process Chapter 4 described. Independent teams checking the same numbers with different assumptions, until a clearer answer emerges, or the case for real significance simply does not hold up under repeated testing. That is slower and less satisfying than a single confirmed headline. But it is the only honest way a claim this large, at this distance, sitting this close to the edge of what current instruments can even measure, was ever going to be settled. Both of those outcomes would still be findings, not failures, and neither one would change anything about the underlying physics from earlier tonight. Even in the most generous reading, where the entire 10 billion light-year excess is exactly as real and as large as first announced, it still was, and always will be, a pattern rather than an object. The same conclusion Laniakea reached at a much smaller scale, now simply pushed out to the largest distance anyone has dared to claim. Set the disputes aside for a moment, and it is worth being precise about the word bound itself, because tonight has been leaning on it without quite pinning it down. A system is gravitationally bound when its own combined gravity is strong enough that its parts cannot escape each other, now or in the future, no matter how much time is allowed to pass. That is a genuine physical test, with a real calculation behind it, not a figure of speech. Astronomers compare two quantities: how fast the parts of a system are actually moving apart or around each other, and how fast they would need to move to escape the system's gravity entirely, the way a rocket needs a minimum speed to leave Earth rather than fall back down. When the actual speeds stay below that escape threshold, the system is bound, and it will hold together, oscillating or orbiting, for as long as nothing external disturbs it. When the actual speeds exceed the threshold, the system is unbound, and its parts will keep separating forever, however slowly. A familiar, close-to-home version of that same calculation makes the idea concrete. Leave Earth slower than about 11 kilometers a second, straight up, and gravity eventually wins, pulling the object back down. Leave faster than that, and Earth's gravity, at that distance, simply cannot catch it. The object keeps going, forever, regardless of how much farther it later slows. Galaxies inside a cluster are governed by exactly the same kind of threshold, just recalculated for a system with far more mass, spread across a far larger distance, and measured in speeds of hundreds of kilometers a second, rather than a handful. The Virgo cluster's own galaxies orbit its center at speeds astronomers have measured directly, through the same redshift technique used everywhere else tonight, and those speeds sit comfortably under Virgo's own escape threshold, which is precisely the calculation that lets astronomers call it bound with real confidence. Not just because it looks dense on a map, it helps to widen the frame slightly before looking at Virgo specifically, because bound systems come in a whole hierarchy of their own, not just two categories of small and large. A star system, held together by a single star's gravity, is bound. A galaxy, held together by the combined gravity of hundreds of billions of stars, along with a great deal of unseen dark matter, is bound at a much larger scale. The local group, a modest handful of galaxies bound to each other, is bound at a larger scale still. Each step up that ladder uses the identical escape velocity test, simply applied to more mass spread across more distance, which is exactly why the test is trustworthy at the very next step up as well. The Virgo cluster, roughly 50 million light-years away, is the nearest large example of a genuinely bound system, one whole size class above the local group. It holds well over 1,000 galaxies, tied together by enough combined mass that their orbital speeds around the cluster's center sit safely under the escape threshold. Astronomers can even watch the boundary of that grip in action. Our own local group sits just outside the Virgo cluster's fully bound region, and is being measurably slowed down in its outward expansion away from Virgo by the cluster's gravity, even though the local group is not itself bound to Virgo and will, on the current evidence, keep drifting away rather than eventually falling in. That slowdown, the astronomers' term for it is infall, is exactly the kind of measurable effect a real gravitational bond produces. Laniakea shows nothing like it. At its scale, no basin-wide slowdown has ever been measured. Galaxies well out toward Laniakea's edges are receding from us at very close to the ordinary rate. The overall expansion of space predicts, with the great attractor only bending, never breaking, their overall retreat. There is a second piece of physics, beyond distance and mass, that makes the difference between Virgo's fate and Laniakea's fate a certainty rather than a coin flip, and it did not enter the story until the very end of the 20th century. Notice too that this same principle already appeared once before tonight, in a smaller, gentler form. The local group's slowdown as it approaches Virgo is a measurable sign of Virgo's gravity reaching out and doing real work on something not fully inside its bound core. That is the middle ground between fully bound and fully unbound made visible. Not every gravitational relationship has to resolve into a clean yes or no immediately. Some, like the local group in Virgo, sit in a slow, ongoing negotiation, one where gravity is currently ahead but has not yet, and may never, close the deal completely, depending on exactly how much mass and time are actually available to it. Two independent teams spent the 1990s chasing the same difficult measurement: the brightness, over time, of a particular kind of exploding star called a Type Ia supernova, a detonation reliable enough in its peak brightness that astronomers can use it as what is sometimes called a standard candle, a light source bright enough and consistent enough to work out a genuine distance from how dim it appears. Both teams expected to find the same thing: a universe whose expansion was gradually slowing down under its own gravity. The way a ball thrown upwards slows as it rises. Both teams, instead, found the opposite. Distant supernovae were consistently dimmer, and therefore farther away than a slowing expansion could explain. The only way to account for the extra distance was an expansion that has been speeding up, not slowing down. One of the two teams was led by Saul Perlmutter, the other by Brian Schmidt, with Adam Rees, a lead contributor on Schmidt's team. Both groups had spent years developing careful techniques for identifying Type Ia supernovae early enough and calibrating their brightness precisely enough for the measurement to be trustworthy at the enormous distances involved. The result, published in 1998, was strange enough that both teams spent considerable effort trying to find the mistake in their own analysis before accepting it. When neither team could find one, and each had independently reached the same conclusion using different supernovae and different methods. The finding held. It earned 3 of the researchers involved, Saul Perlmutter, Brian Schmidt, and Adam Rees, the Nobel Prize in Physics in 2011. Astronomers call the cause of that acceleration dark energy, a name that is honestly more of a placeholder than an explanation, standing in for whatever is responsible for pushing every sufficiently distant region away from every other a little faster with each passing billion years, since its underlying nature is still one of the genuinely open questions in physics. It is worth being fair to how strange this discovery must have felt from the inside. At the time, cosmologists spent most of the 20th century arguing over exactly how much the expansion of the universe was slowing down. Not whether it was slowing down at all, the only real debate was whether gravity would eventually win outright, pulling everything back together in a future collapse, or simply slow the expansion toward an ever gentler coast. An expansion that speeds up was not seriously on the table as an option going into the 1998 measurements. Finding it anyway is part of why the result required such careful, repeated scrutiny before it was accepted, and part of why the 2011 Nobel Prize recognized not just a measurement, but a genuine correction to what nearly every physicist in the field had expected to find. Whatever dark energy turns out to be, its effect on tonight's question is direct and already well modeled. For any two galaxies not already tied together by a gravitational bond strong enough to resist it, the accelerating expansion guarantees, not merely allows, that they will separate faster and faster as time goes on, with no future moment at which gravity gets a second chance to catch up. Bound systems are exempt from that fate because their own gravity has already won the contest, permanently, the way a rock resting on the ground does not care how strong the wind gets. Unbound patterns, including every one of tonight's candidates, are not exempt. Laniakea's slow drift will not merely fail to tighten into a bound structure someday. Given enough time, it will do the opposite. Thin out, its most distant members carried away faster and faster, until the basin that once organized their motion no longer organizes anything at all. There is a middle case worth naming honestly, because the universe rarely sorts itself into only 2 clean categories. Some regions are not yet bound, and not yet guaranteed unbound either, caught in a slower, more ambiguous contest between their own gravity and the accelerating expansion working against it. The outer members of some galaxy clusters sit close enough to that boundary that their long-term fate depends on details, mass distribution, precise velocities that are still being refined survey by survey. Laniakea is not one of these ambiguous cases. Its basin is too large, and its measured drift too gentle relative to its own escape threshold, for the outcome to be in serious doubt. But it is worth knowing the boundary between bound and unbound is not always a clean line drawn in advance. Sometimes it is a genuine contest, decided slowly, the same way any contest between 2 real forces is decided, by whichever one, in the end, simply has more to work with. That is the full shape of the distinction tonight has been drawing since the very first minutes. Bound is not a matter of degree, and it is not a matter of how impressive a structure looks on a map. It is a specific outcome, decided by mass, distance, and time, and now guaranteed one way or the other by the accelerating expansion discovered in 1998. Every pattern described tonight, from the Great Attractor to the Hercules-Corona Borealis Great Wall, sits on the losing side of that test. The local group and the Virgo Cluster and every ordinary galaxy inside both sit on the winning side. The biggest structure in the universe was never going to be an object, because the test for objecthood was decided quietly by physics that has nothing to do with how large a thing is allowed to sound in a headline. Run that guarantee forward patiently, and it points toward a specific, calculable picture of what the universe will eventually look like. One astronomers have already worked out in some detail. Every unbound pattern, every basin, every wall, every filament that is not itself a chain of already bound galaxies and clusters will keep thinning as the accelerating expansion carries its members apart. That thinning does not stop at some natural limit. Given enough time, tens of billions of years and beyond, the members of Laniakea, now drifting gently toward the Great Attractor, will instead be carried away from each other, and from us at ever-increasing speed. Eventually, the accelerating expansion will carry them fast enough that the light they emit today will never reach an observer in our galaxy at all. They will not vanish, but they will pass beyond a horizon no future telescope, however large, could see past. That kind of horizon is not a new idea invented for tonight. It is closely related to the ordinary particle horizon that already limits how far back astronomers can see today. The boundary set by the fact that light, however fast, still needs time to travel, and the universe has only existed for a finite time so far. The difference in the far future is that the boundary stops being fixed. An accelerating expansion carries the horizon inward, region by region, rather than letting it grow outward the way it has for the 13.8 billion years since the beginning. Structures do not need to be destroyed to disappear from view under that kind of horizon. They simply need to be carried, patiently, past a line that keeps closing in. It is only fair to flag the uncertainty riding underneath this whole picture as well, because Chapter 7's discovery of dark energy came with an open question attached that has never fully closed. Whether the acceleration measured in 1998 will continue at a steady rate indefinitely, the simplest and currently best supported assumption, or whether dark energy's strength could itself change over cosmic time, strengthening, weakening, or even eventually reversing. Possibilities some theoretical models allow, but none has yet been confirmed. The island universe future described here is the outcome that follows if the simplest, currently favored assumption holds. It is a well-supported forecast, built on real, repeatedly confirmed measurements, not a certainty carved permanently into the future. Cosmology, like every other science tonight, keeps its confidence proportioned to its evidence and updates it honestly whenever better evidence arrives. What survives that process is precisely the set of systems tonight has already identified as bound. The merged galaxy that the Milky Way and Andromeda will eventually become, together with the smaller members of today's local group gravitationally tied closely enough to come along, and comparable bound systems, clusters like Virgo, scattered elsewhere across the sky. In a 2007 paper, the physicists Lawrence Krauss and Robert Scherer worked through the implications of this in some detail and gave the long-term result a fittingly quiet name, an island universe future, echoing, without quite repeating, a much older phrase. In the 18th century, before anyone had confirmed that the faint smudges called nebulae were separate galaxies rather than clouds of gas inside our own, the philosopher Immanuel Kant speculated in 1755 that each nebula might be a distant, self-contained island universe of stars decades before there was any way to test the idea. That guess turned out to be correct, confirmed conclusively only in the 1920s. Krauss and Scherer's version borrows the same evocative phrase for a related but distinct idea. Not that galaxies are already isolated islands today, but that accelerating expansion will eventually make them so, cutting each bound system off from every other, the way Kant once imagined they already were. Isolated, permanently bound systems, each one surrounded by empty, dark, accelerating space, with the connections between them, the filaments, the walls, the basins, all thinned past the point of being visible, then past the point of existing as a pattern at all. There is something quietly reassuring, rather than unsettling, in how far off that island universe future actually sits. Every measurement tonight has leaned on the redshift surveys, the velocity maps, the cosmic microwave background, the supernova brightness curves, remains fully available today in this comparatively early, comparatively rich era of cosmic history. Nothing about tens of billions of years from now changes a single instrument sitting in an observatory tonight, or a single galaxy currently visible to it. The distant future is real, and worth understanding honestly, precisely because understanding it does not cost anything happening right now. Krauss and Scherer's paper carried a further implication worth sitting with, because it is less about the sky than about knowledge itself. A civilization arising inside one of those far future island galaxies would not merely find the wider cosmic web too faint to see. It would have no direct observational way to reconstruct that the universe had ever been expanding from a hot, dense beginning at all. The light carrying that evidence, including the ancient glow tonight, opened its third chapter with, will itself have thinned past detectability by then, carried beyond the horizon along with everything else. Whatever such a civilization worked out about the universe's history would have to come entirely from records, calculations, and reasoning passed down from a much earlier, much richer era of evidence, an era that, on this accounting, includes the one happening right now, tonight, in whatever room this is being heard in. Nothing about this timeline is unique to some unlucky corner of the universe. The same accelerating expansion applies everywhere, at the same rate, in every direction, which means the island universe future is not a fate reserved for the Milky Way's particular neighborhood. Every bound system, everywhere, ends up isolated the same way, on roughly the same kind of timescale, simply because the underlying physics driving it does not prefer one location over another any more than the cosmological principle from earlier tonight does. It is less a specific prediction about our galaxy than a general statement about what accelerating expansion does to any web of connections, anywhere, given enough time. It is worth being careful about the timescale here, because sleep does not need dread attached to a number this large to be worth the wonder it deserves. The relevant span is not centuries or millennia. It is commonly discussed in the tens of billions of years, dwarfing the roughly 13.8 billion years the universe has existed so far, and it says nothing at all about the fate of the Sun, the Earth, or any single star, all of which run on far shorter clocks of their own. The Sun itself, for comparison, has perhaps another 5 billion years before it exhausts the hydrogen fueling it and begins the slower changes that will eventually end its own ordinary life, a schedule entirely independent of anything Laniakea or the wider cosmic web is doing on a vastly larger stage. It is a statement about the connections between galaxies, not about tomorrow or next year or any human timescale whatsoever, and certainly not about any single star's much shorter, much more immediate story. It is worth marking too how this fits against the very first correction of tonight, back when the difference between a bound galaxy and an unbound pattern was drawn using only distance, mass, and time. Dark energy does not change that test. It simply guarantees which side of it every unbound pattern will eventually land on, permanently, rather than leaving the outcome open to some future rearrangement of gravity's balance. Laniakea was never going to tighten into a bound supercluster, no matter how much additional time was allowed. The accelerating expansion discovered in 1998 is the specific reason the drift dissolves instead of concentrating, the missing piece that turns not yet bound into will never be bound. For every pattern tonight that did not already cross that threshold in its first few billion years, there is a strange, quiet symmetry worth noticing in that eventual picture, one that returns almost exactly to where tonight began. A future observer living inside that merged Milky Way Andromeda galaxy tens of billions of years from now would still see the other bound members of today's local group nearby, close enough that the horizon described earlier in this chapter would never reach them. What would be missing is everything past that small bound cluster. No great attractor to speak of, no basin wide enough to matter, none of tonight's disputed walls, and no cosmic microwave background bright enough to detect either, its last usable photons having redshifted away into undetectability long before that future arrived. That observer would look out and see none of tonight's basins, walls, or disputed great structures. The accelerating expansion will have carried them all past the horizon and thinned what is left of them into nothing worth calling a pattern anymore. That observer's universe would look, for practical purposes, like a single galaxy sitting alone in an otherwise dark and empty sky. Exactly the kind of universe early 20th century astronomers briefly, mistakenly, thought they already lived in, before redshift surveys revealed the web all around us. The very evidence tonight has spent its time on the flows, the basins, the walls, the disputed record holders, is available now specifically because tonight happens to fall inside the narrow, comparatively early window when the universe is old enough to have grown that structure, but not yet old enough for acceleration to have erased the evidence of it. That is not a small thing to have been given. The biggest structure in the universe was never going to be an object, and now it is possible to say something more specific still. It was never going to last either, in any form patient enough to be called permanent. What is available right now, in this comparatively brief window between a nearly smooth early universe and an eventually isolated, quiet one, is a single, honest snapshot of every scale at once. Bound galaxies holding fast at the small end, basins like Laniakea drifting at the middle, and disputed walls, real or partly illusory, stretching out toward the largest distances anyone has dared to map. Tonight is not a tour of permanent monuments. It is a look at a pattern caught, briefly, still legible, on its way to eventually fading from view. There is a version of tonight's answer that could sound, told a little differently, like a loss. Nothing out there is really one thing. The biggest structure in the universe is not really a structure at all, and even the patterns that do exist tonight are already, quietly, coming apart. It is worth spending a little time on why that is not actually the shape tonight has been building toward. Belonging has never required permanence. Not even down here. A family is not a bound object in the sense tonight has been using the word. Its members separate, scatter across cities and years, and the connection holds anyway, through something other than an unbreakable physical tie. A river system is not permanent either. The land it drains can shift, slowly, over geological time, and a watershed that looks fixed on any single map can, given enough patience, redraw itself entirely. Coastlines are the same. The line between land and sea on any map is really a record of one particular moment, held steady only for as long as it takes to draw it, before tides, storms, and slow centuries of erosion quietly redraw it again. None of that made any of them less real, or less worth paying attention to. While they lasted, it only meant the right word for any of them was never object in the first place. It was always something closer to a pattern, sustained by ongoing conditions rather than sealed by a single permanent bond, worth caring about precisely because it takes those conditions, patiently continuing, to keep existing at all. There is a small, deliberate echo worth naming between that patience and the patience the universe itself has shown across the whole of tonight in building anything at all. Gravity did not rush the cosmic web into existence. It worked one small advantage at a time for 13.8 billion years on fluctuations that started at 1 part in 100,000. Astronomers did not rush Laniakea into view either. It took a full career's worth of accumulated redshift and distance measurements before the pattern was clear enough to name. Patience, at every scale tonight has visited, has been the actual mechanism, not a virtue layered on top of the physics afterward. It is fitting, on a night built for rest, that the same quality doing the falling asleep is the one that built the sky being fallen asleep under. Consider, too, what it means that a species confined to one small planet, orbiting one ordinary star, inside one ordinary galaxy, managed to work any of this out at all. Nobody involved in mapping Laniakea has ever left the local group. Every measurement behind tonight was made from here, using light that arrived here, interpreted by minds that evolved here, for entirely different, far more immediate purposes than reading the drift of 100,000 galaxies. That the same minds turned out to be capable of it anyway, patiently, across generations of careful measurement, is at least as remarkable as anything the measurement itself revealed. It is worth returning, briefly, to the very first image of tonight, because it was chosen for a reason beyond convenience. Rain does not need to be told which way to flow, and it does not need to understand gravity, geology, or hydrology to find its river correctly every time. It simply responds to the shape of the ground it happens to be on, faithfully, without effort. Every galaxy in Laniakea is doing something structurally similar, responding faithfully to the shape of the gravitational landscape it happens to sit inside, with no more agency in the matter than a single drop of rain has over which gutter it reaches. That lack of agency was never a small or a cold detail. It is closer to a kind of trust. The universe does not need galaxies, or rivers, or people to understand the rules they are following in order for those rules to hold, gently and reliably, night after night. There is a particular comfort, too, in how ordinary the tools behind tonight's answer turned out to be. Nothing about mapping Laniakea, or the cosmic web, or the record-holding walls required inventing a new kind of physics, or discovering a hidden force nobody had suspected. It required redshift, a technique from the 1920s, a rotation-brightness relation from the 1970s, patient, unglamorous surveying, one galaxy or one quasar or one gamma-ray burst at a time, and enough honesty, once the data was in, to call a pattern, rather than stretch it into an object because the object made the better headline. The universe did not need to be stranger than expected for any of tonight's answer to hold. It only needed to be looked at carefully and described in words that fit what was actually found. The same is true, now, of the address tonight has given the Milky Way. It sits inside a basin with a name, drifting, along with a great many neighbours, toward a shared direction defined by real, measured gravity. That basin will not last forever, and it was never trying to. It is doing, on a scale of hundreds of millions of light years, something closer to what a river does than what a rock does. Organising a flow for as long as the underlying landscape allows it to, and no longer claiming permanence than that. There is something almost domestic in that picture, once it settles. The Milky Way is not adrift in a featureless void, waiting for a bond that will never come. It has a direction. It has neighbours, moving the same way, for reasons that can be measured and mapped, using the same careful mathematics that maps a watershed on Earth. That direction is called home. In the loosest and most honest sense the word can carry at this scale. Not a place that holds on forever, but a place that is, right now, tonight, genuinely shared. There is a specific kind of quiet worth naming in how tonight has treated uncertainty. because it is different from simple doubt. The great attractor's exact distance was given a range rather than a single precise figure. The Hercules-Corona Borealis Great Wall was presented as disputed rather than settled either way. Dark energy was named honestly as a placeholder for something not yet understood. None of that uncertainty was treated as embarrassing or smoothed over for the sake of a cleaner story. It was simply carried openly, the way a careful person carries any honest, not yet known, without pretending it away, and without letting it curdle into anxiety either. That is, in its own right, a kind of rest offered alongside everything tonight has tried to explain. It is worth admitting, too, that tonight has spent a long time on a question that will not change anything about tomorrow. Whether Laniakea holds together for another 100 million years or begins thinning sooner has no bearing on a single ordinary day. Whether the Hercules-Corona Borealis Great Wall turns out to be real or an artifact of a small, difficult catalogue will not alter a single measurable thing about life on Earth. That is not a mark against the question. Most of what makes a fact worth knowing, at tonight, was never going to be its usefulness by morning. It is closer to what a person gets from learning the name of a tree outside a window they have looked through for years without asking. Nothing changes about the tree, or the window, or the view, only about how the looking itself feels from now on. A little less anonymous, a little more specific, a little more like paying attention rather than simply glancing past. There is something almost domestic, too, in comparing this basin to the ordinary places a night can be measured by. A room has walls, and the walls hold their shape for years, decades, sometimes far longer. But nobody expects that permanence from the room to mean anything cosmic. Its stillness is simply useful for exactly as long as it lasts, which is exactly the same relationship Laniakea has with the Milky Way, only stretched across hundreds of millions of light years and measured in a language of redshift and velocity instead of paint and plaster. Scale changes the units. It does not change the shape of the relationship. There is a reason the opening chose a number before it chose a name. 10 billion light years is easy to say and almost impossible to picture, which is exactly the condition every scale in this hour has shared. Too large for the body to feel, small enough for the mind to hold as an idea. Once the idea is given the right shape, that gap between what a number means and what it can be felt to mean is not a flaw in how any of this was explained. It is the ordinary condition of thinking about anything larger than a room, a street, a single human lifetime. The number arrives first. The feeling, if it arrives at all, arrives later, quietly, the way it has been arriving across the last several chapters, not as awe demanded on cue, but as something closer to recognition, settling in on its own schedule. And the disputes from earlier tonight, the Huge-LQG, the Hercules-Corona Borealis Great Wall, are not embarrassments to be quietly set aside. They are what honest science actually looks like at the edge of what current data can settle. A structure claimed at the very limit of detectability, argued over, tested against noise, sometimes confirmed and sometimes walked back, is not a failure of astronomy. It is astronomy working exactly as it should, refusing to let a number sound more certain than the evidence underneath it, even when the number would make a better headline left alone. That same caution is why Laniakea's own boundary and the great attractor's own distance have been described tonight with the hedges they deserve, rather than a false, comfortable precision. It is worth admitting, too, why a word like structure keeps getting reached for at these scales, even by careful astronomers who know exactly what it leaves out. Language built for a human body, moving through a world of rocks, furniture, and other bodies, was never going to have a ready-made word for 100,000 galaxy flow pattern. Borrowing structure and quietly stretching its meaning is simply what any language does when a genuinely new kind of thing needs describing before a genuinely new word has had time to earn its place. The stretch is not a failure of honesty. It is what naming anything new has always required. From the very first time a word for river got reused for something that was not quite a river, or a word for wall got reused for a shape 100,000 galaxies happen to share, what is left, once the exaggeration is set aside and the honest hedges are kept in, is still enormous, still worth the quiet, and still true. 100,000 galaxies moving the same direction as ours, for reasons that were written into the universe within its first fraction of a second and are only now, 13.8 billion years later, measurable from a single small planet inside one of them. That does not need to be a bound object to matter. It only needed tonight to be real. A night sky, looked at plainly, does not show any of this. Stars hang still, or close enough to still that no unaided eye has ever caught one drifting during a single lifetime of looking up. That stillness was never a lie, exactly. It is simply the view from a single vantage point, held for a single human lifetime, far too short and far too fixed to catch 100,000 galaxies in the act of drifting the same direction, or a supercluster's slow structure quietly beginning to thin. Nothing this hour described contradicts the calm of an ordinary night sky. It only adds what the stillness, on its own, was never going to be able to show. Somewhere outside, right now, rain may or may not be falling. It does not matter which, for what comes next, because the image only ever needed to be a rule, not a forecast. Water finds its river without a map, without a plan, and without ever touching the other drops that end up choosing the exact same path. That was the whole shape of tonight's answer, offered before there was time to explain it. And it has held, unchanged, through every scale this hour has climbed since. The Milky Way finds its river too, not a literal one, and not one made of water, but a flow all the same. A slow, measured drift, shared with something like 100,000 other galaxies, all sliding gently toward the same low point in a gravitational landscape. Astronomers gave a name to only in the last few years of a very long history of looking up. That flow has a direction. It has neighbors, it is not going anywhere quickly, and it is not going to last forever, and neither of those facts makes it any less real tonight. It is worth noticing, too, how gentle the whole climb turned out to be in the telling, even though the distances involved keep multiplying past the point where they can be pictured directly. That gentleness was not an accident of style. It followed directly from the physics itself. Nothing in this hour needed alarm, because nothing in this hour described a threat. A pattern thinning out over tens of billions of years is not a catastrophe arriving on any clock worth worrying about. A structure turning out to be a flow rather than a wall is not a loss, only a more accurate description of something that was real either way. The calm was earned by the material, not applied over the top of it. Consider, one more time, and then no more, the full climb this hour has made, because a climb is easier to rest after than a scattering of facts is. It began with rain on a roof, small enough to hold in one glance. It rose to a galaxy, then to the local group, then to a basin 500 million light-years across, then to walls 1 billion light-years long and more, then to the very edge of what the word structure can honestly still describe. Each step used the same rule as the step before it, simply applied at a larger size, gravity, patient and real, doing exactly what it can, and stopping, honestly, exactly where its reach runs out. That is not a difficult shape to hold on to, even now, even this close to sleep. It is closer to a single sentence than to a lecture, and it was always the whole answer, from the very first minute. There is no need to hold on to any of the numbers from earlier. Not the 13.8 billion years, not the 10 billion light years, not the 100,000 galaxies. They did their work already, each one in its own chapter, and none of them needs to be carried any further than that. What is worth keeping, now, is only the shape underneath them. Small things bind, large things drift. And drift is not a lesser fate, only a different one, patient in its own way, honest in its own way, real for exactly as long as it lasts, and asking for nothing more than that. It helps, this late in the hour, to let the record holders go quiet for a moment and just hold the shape of the whole picture at once. Close to home, gravity has already finished its work. The local group, bound, patient, its two largest members, already committed to a slow merger that will not need this hour, or any night like it, to arrive. A little farther out, gravity is still working, not yet finished, not yet certain to win. Laniakea, a basin rather than a body, carrying the Milky Way and something over 100,000 neighbouring galaxies, along a slope rather than into an embrace. Its lowest point, sitting behind our own galaxy's dust, in a direction it took decades of patient infrared and radio work to finally confirm. Farther still, past the edge of anything gravity could plausibly finish, are the walls. Geller and Hutra's first Great Wall, 500 million light-years of real mapped galaxies, found simply by pointing a telescope at one honest slice of sky. The Sloan Great Wall, longer, drawn from a deeper, wider survey a decade and a half later. The Huge-LQG and the Hercules-Corona Borealis Great Wall, larger again, and honestly disputed, sitting exactly where the mathematics of noise and the mathematics of genuine rare structure become difficult to tell apart, however carefully the question is asked. None of them, at any point along that whole climb in scale, was ever going to turn out to be one object. That was decided long before any of them were found, by a test involving only mass, distance, and time, the same test that will eventually, tens of billions of years from now, thin every one of them past the point of being a pattern at all. Somewhere in the middle distance of that whole climb sits the ordinary comfort worth carrying into sleep tonight. None of it required a rescue or a discovery of something hidden and strange to become worth caring about. The great attractor was ordinary matter behind ordinary dust. Laniakea was ordinary galaxies, already catalogued, simply watched carefully enough, for long enough, to reveal which way they were leaning. Even the disputed walls were built from real telescopes, pointed carefully at real coordinates, by people who cared enough to check their own excitement against the data twice before publishing it. Nothing in this hour needed to be more than that. It only needed to be true and patient, and looked at closely enough to be understood a little more clearly than it was an hour ago. What is left, once all of that settles, is not a smaller universe than the headlines promised. It is a more honest one, and honest was always going to sleep better than impressive. The biggest structure in the universe is not really an object, and it never needed to be worth an hour of quiet attention. 100,000 galaxies, hours among them, agreeing, right now, on which way is down. There will likely be another headline, at some point, claiming something larger still. A new survey, a new catalogue, a new algorithm run with a slightly longer linking length, somewhere finding a pattern wide enough to beat 10 billion light-years. It will very likely turn out to be exactly what every candidate this hour has walked through turned out to be. A real, honestly measured overdensity, or a shape drawn generously through noise, or something sitting, uncomfortably and honestly, in the narrow space between the two. Either way, the test that decides whether it counts as an object will not have changed. It never depends on the headline. It only ever depended on mass, distance, and time, quietly doing their own accounting, long before any astronomer got around to giving the result a name. It is worth carrying one last piece of arithmetic into sleep, not to solve anything further, only to feel its shape once, gently, before letting it go. Mass, distance, and time. The same three quantities, applied over and over, across every scale visited tonight, deciding every single time whether something held together or drifted apart. Small mass, short distance, long time available, bound, patient, permanent, the way the local group is bound. Enormous mass, enormous distance, not remotely enough time, unbound, drifting, temporary, the way Laniakea drifts, the way every wall past it drifts, the way the whole cosmic web will eventually, softly, come undone. The same three numbers, quietly doing the same accounting, at every size the universe happens to offer. There was a small warning near the very start of the hour, easy to miss under everything that followed it. Worth returning to now that it has been earned, rather than simply promised. The largest things astronomers describe are not false, or exaggerated, or made up for a headline. That warning was not a hedge, added out of caution. It turned out to be the entire shape of the answer, restated quietly at the end of every chapter since. The great attractor is real. Laniakea is real. The walls, disputed or not, are built from real measurements of real objects. However far the linking algorithms sometimes reach to connect them, what was never real, at any point in the climb, was the assumption sitting underneath the word structure itself. The quiet expectation that big enough had to mean bound enough, that a name and a size were the same thing as a body. Let the numbers go now. They have done their work. What is left is only the shape, a basin, a slope, a shared direction, wide enough to hold 100,000 galaxies, and small enough, still, to be described in a single unhurried breath before sleep. Somewhere behind the dust of our own galaxy's disk, in a direction the eye will never quite reach, the deepest part of that basin sits, pulling gently, patiently, on everything nearby, including the room this is being heard in, including the body lying still inside it, including the slow, unhurried breath that room is about to settle into. The rain outside, if there is any, has already found its river. The galaxy outside that, if you could see far enough past the dust, has already found its basin. And the body here, right now, warm and unhurried, has already found the rest it was reaching for the whole time this hour has been quietly circling closer to it. There is nothing more to explain tonight, and nothing left that needs to be understood before sleep can arrive on its own. The basin will still be there tomorrow, patient, unbound, doing exactly what it has always done, not holding anything together forever, only ever agreeing, gently, on which way is down, and letting everything nearby drift along with it for as long as it lasts. That is enough. That was always going to be enough. The universe will still be here when you wake up. So will we. Good night.